All right, so on the screen here, I have a sketch of the volume versus temperature for an ideal or real gas, not ideal. We'll explain the difference in a second here. Um, at a constant pressure, okay? So let's highlight that because it does make a difference. So a lot of these ideal gas law things were the reality of it is we can approximate things, but the universe is very dynamic. So here in this one, the pressure is constant. Okay, and so you see a linear straight line there, and that represents the ideal gas behavior. Our x-axis is the temperature. As the temperature increases, and the y-axis is the volume, but there is a direct and positive relationship between an increase in temperature and an increase in volume with regards to the behavior of the gas. So the line extrapolates to zero volume at negative 273.15 Celsius, which is absolute zero. So that would be 0 Kelvin when the gas becomes a liquid. However, the volume actually decreases at a liquefaction point. And so then the volume decreases slightly once the substance is a solid, but never becomes zero. And so there is this one area right here where something freezes, right? Where it condenses to form a liquid, and there's a part where it freezes to form a solid. Okay, and this is, in general, this is just one example. All right, so then let's go to the next slide. On the next slide, there are two diagrams. Again, in this case, this is an interesting one because we have pressure for our y-axis, we have volume. So for diagram A, the first diagram, each curve, isotherm, represents the relationship between the pressure and the volume at a fixed temperature. The upper curves at the higher temperatures, so these are basically what we're looking at. Let me put on my little pointer here. Turn on the pointer. So this region right here is the region of interest. So liquid, and here we're gonna, anytime we talk about gas, if I accidentally say gas, I'm referring to vapor, right? So these things are a unique shape that you see a lot of, but basically as you increase the volume and you increase the pressure and you increase the temperature, at some point, if you increase the pressure and temperature too high, whoops, I got ahead of myself, then you cannot form a liquid. And then if you increase the volume without increasing the pressure, there's this barrier. So the barrier between the liquid and the vapor is this little section right here, and that is what we refer to as the liquid vapor region. Okay, and there's usually, if we look to the right, there's kind of this critical point. And so, oops, I lost my little thing. My critical point here, oops, what is going on? That helps us to distinguish what is the liquid region, what is the vapor region. Well, this is true, it's not an ideal gas. So things are dynamic. So part A, basically, the lower curves are not hyperbolas. A hyperbola in a mathematics perspective is something that kind of curves like this and then curves like this. So it's not a perfect curve. In other words, here this is a hyperbola, this is a hyperbola, not to be confused with hyperboles. But then at some point they lose the curve, right? And so when we graph the temperature versus the pressure versus the volume, you'll see this shape or pattern emerge. And that's how we determine the liquid vapor region. In diagram B, we've expanded that portion so you can kind of see where the phase can change from gas to liquid. The proper term for gas, again, we're going to start using the term vapor, and that refers to the gas phase when it exists at a temperature below the boiling temperature. So a lot of the things when we talk about boiling temperatures and freezing temperatures, we're talking at 1 atmosphere, which is the pressure that you feel in the atmosphere. So there is a little bit of pressure. And then if you increase the pressure, obviously that has an impact. If you increase the volume of the space that the gas takes up, that can have an impact. If you decrease the volume, that can have an impact. And so if we zoom in, so B is like a zooming in of this region here, we see that there is a critical point, which is like the top of this hill, where lots of stuff happens. This is the saturation curve, and this is where a liquid slash vapor can kind of exist. The critical point, the curve for that is the critical isotherm. So there's a temperature that operates in this space. So this temperature varies. This red line varies its curve based on the amount of volume you have. So if this is your volume and this will be your pressure, this would be where let me just draw it out so you can see a little better. So in other words, this critical isotherm or temperature occurs when you have this as your volume. So this could be a volume critical here. And then if you extend that all the way over here, this would be like your pressure critical. And those values can change, right? And this all has to do with the ideal gas law. And then the curves over here, the gas isn't considered to be ideal. So ideal is like atmospheric stuff, and there are exceptions to ideal gases, basically. All right. And so here are some critical temps and pressures. This is just a short list. So the critical temperature then for water is, well, it's just a little bit over boiling, right? Well, actually, it's way over boiling. It's 374 degrees Celsius. And then that pressure is 219 atmospheres. And then this would be the conversion in pascals. Okay, and so this is like sulfur dioxide, carbon dioxide, a little bit lower, lower temps here, lower pressure here. And so this is the pressures and temperature where you'll see these critical points. So if I go back one slide, that critical point, there's going to be a temperature that's associated with the pressure. And that's what that, and you'll probably use this for your homework, not in this section, but for the next section. So the full, this full table is in the actual online textbook, so just see that. The next thing we want to talk about, so whenever I have a pressure versus temperature diagraph, and this is one for water, so let me just mention that this is for water, right? We can kind of see, note that the axes are nonlinear and that the graph is not to scale, right? So in other words, like the distance between here to here and from here to here is not scaled properly, and this is not scaled properly, but we draw it this way. But there's a region, so this region right here, we'll kind of highlight this in a different color, I suppose. So this region right here would be like solids, right? And then this region over here would be like when water would be a liquid. And then this region over here would be when it's like a vapor. Whoops, gotta undo that one. Actually, that needs to be a different color, so I'll make that. Boop. And so this would be where it would be a vapor. And so there are temperatures and pressures, and based on whatever the temperature and pressure is, it could be a vapor, it could be a liquid, or it could be a solid. But the triple point is when it can be all three. And so the triple point is where they all three converge. So note that the axes are nonlinear and the graph is not the scale, and that this graph is simplified. There are several other exotic phases of ice at higher pressures and stuff like this. But then also there is the critical point as well, which is important. So the triple point's an interesting thing. Why does this matter? Because sometimes in a lab you can increase the pressure or decrease the pressure, and that allows you to do certain things. And here are some triple point temps and pressures. So for water, and this is right from that diagram that we had the last time. For water, the temperature is 273 degrees Kelvin, which is just a little bit over zero, right? So just a little bit over zero, that's where it can start to melt, right? But that is rated at a very specific pressure, right? So there's different parts to that. Oops. All right, and then here are some more common ones. Again, this whole table is posted in the online textbook. But if you increase the pressure, that has in other words, if you have a lot of pressure, you can almost force the molecules together. And you can keep it a solid, or you can melt it, right? So sometimes if you increase the pressure, it melts the water into a liquid. And then there's other parts where you can leave it a liquid at a higher temperature if you increase the pressure. So for example, if we look in this space over here, I gotta change, that's in my way. So if we look at this space right here, normally a liquid turns into a gas. This is at normal. If you look here, that's 1 atmospheric pressure. At normal atmospheric pressure, a liquid at 100 degrees Celsius becomes a vapor, right? That's the boiling point. But if you increase the pressure to up to 218 atmospheric pressure, right, it can remain a liquid at a higher temperature. In fact, it can remain a liquid until about 373 degrees Celsius. So by increasing the pressure, you can keep it a liquid for a little bit longer, and so that's the triple point diagram and the relationship between pressure and water vapor. So let's unpack these two diagrams. So right at the boiling point, you have this thing called equilibrium. And so equilibrium occurs, and so let's just talk about the diagrams, and I'll write some notes here. So in diagram A, right, the rates of the boiling point and condensation are equal. So condensation is when something's a gas and it starts to become a liquid, right? So right here you have some vapor, and then it condenses and becomes a liquid. And then you have liquid, and it gets some extra kinetic energy, and it becomes a vapor. So you can have this state of equilibrium where you lose water to water vapor, but then also you gain water because some of the water vapor condenses down to be water. And this usually, and so the rates of boiling and condensation are equal to each other. We call this equilibrium. So when you see that, that's called equilibrium. It's when your vaporization equals your condensation. So you don't lose, you're not losing liquid to gas, right? So you're going from a liquid, oh shoot, I hate this pen, to a vapor, but then also due to condensation, you're going from a vapor to a liquid. So the liquid remains about the same, and then the vapor remains about the same. And then in B, at a higher temperature, the boiling rate is faster, and the rates at which the molecules leave the liquid enter the gas also faster. Because there are more molecules in the gas pressure is higher, and at a rate in which the gas molecules condense and enter the liquid faster. So there is a result of gas and liquid that are also in equilibrium at a higher temperature. So what they're saying is at a higher temperature you have the same thing, but now you have a higher rate of vaporization, but there's some stuff going on here that also causes you to have a higher rate of condensation. Now there is a point where you can have a very high rate of vaporization and a very low rate of condensation, and vice versa. You can have condensation at a higher rate than you have your vaporization. So you can have a vaporization that's like this, and then you can have condensation that's much larger. This is not equilibrium. So, oops. I'm going to have to erase it all. So this is equilibrium because they equal, but if you have one longer than the other, or if you have this one longer than this one, this is not equilibrium. This right here is equilibrium because the vapor is equal to the condensation. So that's a little clue for the homework. You're not going to have any homework over this section, but these concepts are important for the next assignment that you have. And that's basically it, okay? Yeah, and then also play with this FET thing. So in the textbook, if you go back here, they have this FET simulator, and I like this, and I'm going to open this in. So this is a simulator that kind of shows you the relationship between these. Hold on. States of matter. So I'm going to do this states of matter. And this is really nice because you can see the relationship between the kinetic energy of the molecules and how it impacts you know, how the pressure and the volume and the temperature are all kind of connected along with the kinetic energy. I gotta go back one. I just want the simulator. No, I want the other simulator. But that one's a good one. You should play with that one too. We'll do the basic one first, and then you can do the second one. And I'll put these links in Canvas. This is fine. So let's do this one. Right? And so phases and phase changes. So the first thing are the states, right? So if I put a solid in there, notice that the molecules are close together. If I make it a liquid, they spread out a little bit. If I make them a gas, they're all over the place. And so I have some choices here. I could choose water. So these are little water molecules, right? And a vapor thing. And so notice that the temperature is like really high. Well, what I can do is I could lower that temperature, and as I lower the temperature, you can see how the molecules start to slow down. I can lower it a little more. I could lower it quite a bit, and as I just lower the temperature, the molecules start to slow down. And I want you to look at some of these critical points. Now, this is assuming the volume and the pressure stays the same, but see how they start to fall down to the bottom? Well, they'll turn into a liquid, right? At a certain point. And then I can even make them turn into a solid. And so if I just keep decreasing the temperature, an absolute value of 0 will cause them to not be able to move at all. Right? So if I bring that down to 0 Kelvin, this is absolute 0. There's no motion. So see how they're vibrating a little bit? If I bring that down to 0, I don't know if the simulator will let me. Yeah, it won't let me. But there's very little movement. Then if I heat them up, then they start to move again. So that's that relationship between thermal energy and kinetic energy. But it also has an impact on whether it's a liquid. They still move when they're a liquid. In fact, they still move when they're a solid. Okay, so that's one thing that's kind of neat. And then you could do that like, well, what is it with oxygen? Well, oxygen's a solid here, right? That's very cold, right? So then as I heat it up, so at room temperature, remember room temperature is about 273 degrees. It's actually 293 degrees. So oxygen is still kind of like a liquid, but it almost enters the gas phase, but it's at a higher temperature, right? And so those are the different things that you could think about. If I want to go to phase changes, now this is a nice one because you can look at that phase diagram that we were talking about. And so I can increase the pressure, and then I can also decrease the volume. So I'm going to put water in there. If I increase or decrease the volume, right, and I keep going, and I keep going, and I keep going, notice that my pressure is increasing. Why? Because the molecules are bouncing off, right? So this is really, and then if I keep, now my atmospheric pressure is crazy. This is almost behaving like a liquid, but see, it's right here on this liquid border with gas. So this is where this is our position here. Now, if I cool it off, it'll go more towards the liquid, right? So if I cool the temperature down, notice that my pressure starts to come down, and I go back towards the liquid side. Okay? But if I increase the pressure, right? If I increase the pressure, so now I've really cranked the pressure up. But it's still riding this liquid gas because it's kind of in an equilibrium. Now if I change the volume, notice that my pressure goes down. And then now the water molecules have more room to move. Okay? And boiling is 273 plus 100, so it's already at boiling point, so this should be a vapor. But if I cool it off, the pressure goes down, and I can make it look like a liquid. So this is like liquid water. Notice that they're sticking together, but none of the molecules are escaping. So this is like liquid, and if I condense it down more, I can actually freeze it. So at 273, I think it is the boiling, or is the freezing point. So they'll stick together till I get to about 273, which is when it would melt. So see my temperature in Kelvin, which is 0 degrees Celsius. So I'm just heating it up a little. If I go, there you go. So I got one rogue molecule that escaped, but now it's coming back down. And this happens naturally, right? If I decrease the pressure, though, that can have an impact on it too. So anyways, just play around with that. I want you to see the relationship of that. That's all I got for today.